You know what really bothers me? It's this idea that when something falls into a black hole, it just keeps falling inward, tumbling through empty space toward some inevitable crushing point at the center. We picture it like falling down a well or sinking to the bottom of the ocean. That's the image almost everyone has. And I've got to tell you, as far as modern physics is concerned, that picture might be completely wrong. Let me back up for a second. When we talk about black holes, we're usually imagining them from the outside. We see this dark sphere in space, light bending around it, maybe a glowing disk of hot gas swirling before it disappears past the point of no return. We call that boundary the event horizon. And we think, okay, past that horizon there must be an interior, a volume of space inside, like the inside of a balloon or a cave. That seems obvious, right? If there's a surface, there's got to be something on the other side of it. But what if I told you that this whole notion of an interior might be an illusion? What if the black hole doesn't actually have an inside in the way we think about insides? Now, I'm not saying this to be mysterious or provocative. I'm saying it because when you take quantum mechanics seriously, when you really think about information and entropy and the way space-time behaves near extreme gravity, you start to realize something deeply strange. The black hole might be more like a hologram than a container. Everything that seems to fall in might actually, in some sense, never leave the surface. Let's think about what we know for sure. General relativity tells us that a black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. That much is solid, well-tested physics. Einstein's equations describe how mass warps space-time, and when you compress enough mass into a small enough region, you get a black hole. The math works beautifully. It predicts things like gravitational waves, which we've now detected, so we trust the framework. But here's the thing. General relativity, on its own, describes the black hole as having a definite interior. If you were to fall past the horizon, according to Einstein's equations, you wouldn't even notice the moment you crossed it. You'd just keep falling, and eventually you'd hit the singularity, a point where the equations break down and densities become infinite. That's the classical story. And for a long time, that's what we thought happened. Then quantum mechanics enters the picture. And quantum mechanics has this fundamental principle. Information can't be destroyed. If I burn a book, the information in that book isn't gone, it's just scrambled into the smoke and ash and radiation. In principle, if you were clever enough and had perfect knowledge of all the particles, you could reconstruct what the book said. That's what it means for physics to be reversible at the quantum level. Every process has to preserve information. So what happens when you throw that book into a black hole? According to the old view, the information falls past the horizon, tumbles toward the singularity, and then what? It's gone. But Stephen Hawking showed in the 1970s that black holes aren't completely black. They emit radiation, now called Hawking radiation, because of quantum effects near the horizon. And here's the kicker. As far as anyone could tell, that radiation was completely random, totally thermal. It didn't carry any information about what fell in. The book's information would be lost forever. This caused a crisis, a real crisis. If black holes destroy information, then quantum mechanics is wrong in a fundamental way. But we've tested quantum mechanics in every conceivable scenario, and it always holds up. So either we're missing something about black holes, or we're missing something about quantum mechanics, or both. Now let me tell you what some of us started thinking about in the decades that followed. We started asking, what if the information doesn't actually fall into the interior? What if it never really goes inside at all? What if the horizon itself, that boundary, is doing something much more interesting than we thought? There's this thing called the holographic principle. It's one of the most radical ideas to come out of theoretical physics in the last few decades. The rough idea is this. All the information about what happens inside a volume of space can be encoded on the boundary of that volume. It's like how a hologram on a flat piece of film can contain a three-dimensional image. The information isn't stored in the volume, it's stored on the surface. Jacob Bekenstein and Hawking had already noticed something curious. A black hole has entropy, a measure of hidden information, and that entropy is proportional to the area of the event horizon, not the volume inside it. That was weird. If you think about normal stuff, like a box of gas, the entropy depends on the volume, on how many particles are bouncing around in there. But for a black hole, it's all about the surface area. Why? What if it's because there is no inside, not in the usual sense? What if the black hole is fundamentally a surface phenomenon, and all the information about everything that ever fell in is somehow encoded on the horizon? This is what the holographic principle suggests. And if that's true, then when we talk about the interior, we might be talking about a kind of illusion, a way of describing the same information from a different perspective. Let me try to make this a bit more concrete. Imagine you and I are watching something fall into a black hole. From our perspective, far away, we see the object slow down as it approaches the horizon. Time dilation gets more and more extreme. The object gets redder, dimmer, and it takes longer and longer to fall that last tiny bit. In fact, from our point of view, it never quite crosses the horizon. It just freezes there, asymptotically approaching the boundary, fading away into the Hawking radiation. We see the information smeared out over the horizon, thermalized, scrambled, but still there. But what if you're the one falling in? Well, according to general relativity, you'd sail right through the horizon. You wouldn't feel anything special. You'd look around and you'd think you were inside the black hole, falling toward the singularity. You'd experience an interior. So which is it? Is there an interior or not? This is where things get truly strange, and we have to be very careful. One leading idea coming out of something called the ADS-CFT correspondence and other work in string theory and quantum gravity is that these two descriptions are actually the same thing, just viewed from different perspectives. The exterior observer's description, where everything stays on the horizon, and the infalling observer's description, where there's an interior, are both valid, both real in their own contexts, but they're not describing two separate realities. They're two different ways of talking about the same underlying quantum information. This sounds like nonsense at first. How can there both be and not be an interior? But think about it this way. In quantum mechanics, we're used to the idea that the same system can be described in different ways, depending on what you're measuring, what reference frame you're in. The interior might be what we call an emergent description. It's a useful way of organizing the information if you're falling in, but it's not fundamental. The fundamental degrees of freedom, the real quantum bits of information, live on the horizon. Now, I want to be really clear about something. This is theoretical. We don't have direct experimental proof of any of this. We can't go to a black hole and check. What we have are mathematical arguments, consistency checks, and deep principles like the holographic principle that seem to be telling us something profound about the nature of space-time and information. As far as we know, these ideas are on the right track, but there's still a lot we don't understand. One of the big puzzles is something called the firewall paradox, which came up about a decade ago. If information really is preserved and comes out in the Hawking radiation, then there are certain quantum properties called entanglement that have to be respected. But if you work through the math carefully, it seems like the horizon can't be both a smooth, harmless place that you can fall through and a place that preserves all this entanglement structure. Something called complementarity was supposed to resolve this, the idea that different observers see different things and that's okay. But the firewall argument said, wait, maybe the horizon isn't smooth at all. Maybe when you get close, you hit a wall of ultra-high energy radiation and you're incinerated instantly. That would solve the information problem in a brutal way. Nothing falls inside because nothing can get past the firewall, but it would also mean that general relativity's prediction that you can fall smoothly through a horizon is wrong in a dramatic way for large black holes. And that seems hard to swallow. We've built a lot of physics on the equivalence principle, the idea that if you're in free fall, you don't feel gravity locally. A firewall would violate that. So where does that leave us? Honestly, it leaves us with a lot of open questions. Some physicists think the firewall is real. Others think there's a subtle resolution where complementarity still holds, where the interior is real for the infalling observer, but the information is also on the horizon for the outside observer, and there's no contradiction because the two descriptions can never be directly compared. You can't fall in and then come back out to compare notes, after all. What really strikes me about all this is how it challenges our basic intuitions about space. We think of space as this thing that's just there, a stage where physics happens. You have points in space, regions of space, and objects move through it. But quantum gravity seems to be telling us that space itself might be emergent, built up from something more fundamental, something like quantum entanglement or information. The interior of a black hole might not be a pre-existing place that you fall into. It might be a description that only makes sense from a certain perspective, constructed from the pattern of information on the horizon. There's a beautiful idea that comes out of the ADS-CFT correspondence, which is a specific realization of holography. In that framework, you can have a space-time with gravity, including black holes, and that entire space-time, including its interior, is exactly equivalent to a quantum theory living on the boundary of that space, a theory with no gravity at all, just quantum fields. The interior geometry, the black hole, the whole thing, emerges from the way those boundary quantum fields are entangled and evolving. The interior doesn't have an independent existence. It's a way of describing the correlations in the boundary theory. If that's true more generally, and a lot of us suspect it is, then the question, does the black hole have an interior, might be the wrong question. It's like asking whether a shadow is really there. Well, it depends on what you mean. There's a pattern of darkness on the ground, and we call it a shadow, and it's useful to talk about it that way. But it's not a thing in itself. It's an effect of light being blocked. Similarly, the black hole interior might be an effect, a way of talking about the organization of information and entanglement on the horizon, useful from certain perspectives, but not fundamental. I think what really gets me about this whole line of thought is the implications for the nature of reality. We're used to thinking that if we can't see inside something, it's just because we lack access, but the inside is still there, still real, still doing its thing. But quantum mechanics and gravity together seem to be hinting that observation and access are more fundamental than we thought. The interior might only exist relative to an observer who falls in. From the outside, it's not there. And both of those statements can be true. This ties into deeper questions about the emergence of space-time. If space is emergent, if geometry comes from entanglement, then the whole idea of a region of space having a definite interior is suspect. There's a phrase I've heard, the geometry is the entanglement. The way bits of space are connected, the way you can move from one place to another, might all be a reflection of how the underlying quantum information is correlated. We see hints of this in the ER equals EPR conjecture, the idea that entanglement between particles, which Einstein called spooky action at a distance, might actually be describing tiny wormholes, Einstein-Rosen bridges, connecting those particles through space-time. If that's right, then space-distance connection, all of it is built from entanglement. And a black hole, which is an extreme case of entanglement and information processing, might be the clearest place to see this. But I want to be honest about the limits of what we know. We don't have a complete theory of quantum gravity yet. String theory is a candidate, loop quantum gravity is another, and there are other approaches. They all agree that something radical happens at the Planck scale, the tiny scale where both quantum mechanics and gravity become important. But we don't have direct experimental access to that regime. We have to reason our way there using consistency, mathematical beauty, and extrapolation from what we do know. Black holes are our best laboratory for these ideas, because they're places where gravity becomes strong enough that quantum effects can't be ignored, but they're also, in principle, something we can observe in the universe. We've seen the shadows of black holes. We've detected gravitational waves from black holes merging. We're getting better at studying them, and maybe, just maybe, in the details of Hawking radiation or the way information comes out, we'll find evidence for these strange ideas. What would it mean if black holes really don't have interiors in the classical sense? It would mean that space-time is not fundamental. It would mean that our everyday experience of moving through space, of things being inside other things, is a kind of approximate description that works well in ordinary circumstances, but breaks down in extreme ones. It would mean that the universe is far stranger and more deeply quantum than we've imagined. And yet, from another angle, it would be a triumph. It would mean that the principles we've discovered, information conservation, holography, the deep connection between entropy and area, are real guides to the underlying structure of reality. It would mean we're on the right track, even if the destination is somewhere we never expected. So, do black holes have an interior? The answer, as far as modern physics suggests, is both yes and no, depending on who's asking and how you define interior. For someone falling in, there's an interior, at least in their experience. For someone outside, the interior might be a redundant description of information that's really on the horizon. And the deep truth might be that the question itself assumes a classical picture of space that doesn't hold up under quantum scrutiny. I find that unsettling and exhilarating in equal measure. We're probing the foundations of space and time, and what we're finding is that they're not as solid as we thought. They're emergent, provisional, perspective-dependent. The black hole, that most mysterious object in the cosmos, is teaching us that reality is far more subtle than the picture we see with our eyes, and we're still learning, we're still arguing, calculating, proposing new ideas, testing them against what we know. That's what makes this exciting. We don't have all the answers, we might never have all the answers, but we're asking better questions, and that, in the end, is what physics is about.